Okay, so let's review what we've been looking at in the past two sections, the product quotient rule and the derivatives of trig functions, with some problems on a worksheet here. Okay, so let's try these. All right, derivative of each function. Okay, so I want to find f prime here. So again, first thing I look at is what's the structure of the function. I see a product. Okay, so I have a product of two functions of x, so I have to use the product rule. So, derivative of the first, so the derivative of the x squared minus 2x is 2x, times the second as it is, plus first as it is, x squared minus 2, times the derivative of the second, but the derivative of 3x minus 5 is just 3. Okay, and then I just multiply this out and clean it up. All right, so I get 6x squared minus 10x, distribute the 3, so plus 3x squared minus 6. So I get 6x squared plus 3x squared is 9x squared minus 10x minus 6. There you go. All right, b here. Again, that's another product. That's a product of two functions of x. So when I do g prime here, derivative of the first is 3x squared, times the second as it is, cosine x, plus first as it is, x cubed, times the derivative of x cubed, which is minus sine x. So I get 3x squared cosine x minus x cubed sine x. And again, that might be fine. I might want to go ahead and do some factoring, as I will in the future. And I might want to say I could take out x squared, and I get 3 cosine x minus x sine x. Okay. So now either one for this purpose is okay, because we haven't said what we want to do with this. All right, so now I look at the structure of this and I see a quotient, function of x over a function of x. Okay, so f prime of x, I'm going to use top and bottom. Derivative of the top, which would be 1, times the bottom as it is, 4x minus 3. Minus, in the quotient rule, top as it is, x plus 3, and derivative of the bottom is 4, over the bottom squared. Okay, so I just clean this up a bit. I get 4x minus 3, and then I essentially have a minus 4 that has to be distributed to each place here. So minus 4x minus 12 over 4x minus 3 squared. And indeed, we do see that cancellation here of the x terms in the numerator, but I do end up with minus 15 over 4x minus 3 squared. Okay, here's another quotient, sine x over x squared. So y prime, derivative of the top is cosine x, times the bottom as it is, x squared, minus top as it is, sine x, times the derivative of the bottom, 2x, over the bottom, x squared squared. Okay, so I'm going to get x squared cosine x minus 2x sine x over x to the 4th. Now here's a place where I can see I have some x's everywhere, so it might help to factor a bit. X times x cosine x minus 2 sine x over x to the 4th. And what I see is I can cancel one of the x on top with one of the ones on the bottom. So I'll end up with x cubed down there. And I have x cosine x minus 2 sine x still over that x cubed. All right, so now you see the benefit of looking for some canceling and doing some factoring and looking for canceling. If I had to do another derivative of this, say, it would be a lot easier from that final form. Or if I had to find out when this was 0, it would be easier. All right, so there is some benefit to this. Okay, another derivative. But what do I see? I see a quotient. So f prime of x, derivative of the top, cosine x, times the bottom as it is, 1 minus cosine x, minus top as it is, sine x, times the derivative of the bottom. But the derivative of the bottom, the 1 goes away to 0, and then I have derivative minus cosine x. So I have minus, and then the derivative of cosine x, but that's minus sine x. So the minuses are going to cancel, and I'm going to get just sine x all over 1 minus cosine x squared. Okay, so let's see if this cleans up at all. All right, so in the numerator, I'm going to get cosine x minus cosine squared x minus sine squared x all over 1 minus cosine x. Okay. Now, notice the top is actually cosine x minus, and then if I group that, cosine squared x plus sine squared x. So I took out the minus sign out of this to put it in parentheses. Over, whoops, I forgot the squaring on the 1 minus cosine squared. Over 1 minus cosine x squared. But remember, trig identity. This cosine squared plus sine squared, that's 1. So I get cosine x minus 1 over 1 minus cosine x squared. Okay. But what I can do is that 1 minus cosine x squared in the bottom, so it doesn't matter, I could do cosine x minus 1 over cosine x minus 1 squared because it's squared, so that it doesn't matter if I change the order of the difference down there. And we see one of them is one, I have a cosine x minus 1, one of them on top of two of them, one can cancel. I get 1 over cosine x minus 1. All right, so you see that beyond that first step there, you see all the benefit of what all that manipulation gets you in the end is to a nice condensed form. Okay, continuing on here, let's take the derivative of y equals tan x plus 2 cotan x. All right, so these are being added, so I'm just going to do these one by one. Derivative of tan x is secant squared x, plus I have a multiplying 2, and then the derivative of cotan x is, so derivative of tan is secant squared, derivative of cotan is cosecant squared with a minus. So I'm going to change that plus to a minus, and then put cosecant squared. Okay? And yeah, I'm going to leave it like that because I don't see much benefit in doing anything with that. Okay. All right. G of x equals e to the x cosecant x. All right, don't be drawn into the cosecant yet. First thing I need to notice is this is a product. Okay, the product of e to the x times cosecant x. So the first thing I'm thinking is I have to handle a product rule. So derivative of the first, derivative of e to the x is just e to the x. Second as it is, cosecant x. Plus, first as it is, e to the x, derivative of cosecant x. Okay, secant gave me secant tan. Cosecant gives me cosecant cotan with a minus. So change that to a minus. and I get minus cosecant x cotan x. All right, now that looks to me like I should do some factoring because I have an e to the x in both, I have cosecant x in both. So if I take out an e to the x cosecant x, then inside I have 1 minus cotan x. And that looks like a much nicer final form there. Okay, I want to take a good look at this last one here because it has a lot of good information in it. Determine the point or points at which the graph of the function has a horizontal tangent line. Okay, so we're given y equals x plus sine x on x between 0 and 2 pi. All right, so here's the interesting thing. We've been focused on taking derivatives. We can't forget that the derivative, again, equals the slope of the tangent line. All right, so if we have a horizontal tangent line, that's a slope of the tangent line equal to 0. So this question is really asking, when is the derivative equal to 0? Okay, so that's just a restatement of the whole problem here. I want to know when is the derivative equal to 0. Okay, so I put that thought in the side of my mind, and I go and I find the derivative. Okay, y is x plus sine x. Y prime is then, derivative of x is 1, plus derivative of sine x is cosine x. Okay, and so I'm actually asking, when is 1 plus cosine x equal to 0, specifically on that interval? And so I would actually have cosine x equals minus 1. All right, when is cosine x equal to minus 1? So there's my unit circle. Cosine is how far you go out, so that would be going out here. This would be this point here. So that is at pi. Okay, so cosine x for this interval is equal to minus 1 when x is pi. And there's how we found that. So we can't forget that the derivative is the slope of the tangent line. We're using all these different ideas to find the derivative. Now, once we get past finding, getting comfortable with doing the derivatives, then we get more into talking about what we're going to do with the derivative. Use it as a slope of a tangent line. So that's a very important point for us.